The open ocean is an actively hostile environment. Any vessel attempting to cross it must survive the constant brute force of massive waves and highly unpredictable weather. Now, imagine navigating those conditions while carrying millions of gallons of unrefined crude oil. This is the job of ultra-large crude carriers. Unlike smaller product tankers that move refined oil to local markets, these massive ships transport raw crude directly from global extraction points to distant refineries. Operating this floating industrial site requires a specialized crew of about 30 people. They eat, sleep, and work inside the ship's accommodation area for months at a time. Because of the intense volatility of the cargo and the isolation of the open sea, the crew operates under constant danger, requiring specialized enclosed emergency escape boats for life-threatening scenarios. The core physical problem is simple but deadly. Carrying millions of gallons of highly flammable liquid across an ocean in a single giant steel tub is a recipe for disaster. Surviving the physics of the open ocean requires a vessel designed around total structural compartmentalization and precise internal balance. When sloshing oil shifts the ship's center of gravity, it slams force against the hull. In an undivided tank, this sudden weight transfer causes capsizing. By dividing the hull into smaller cargo tanks, the physical impact is fragmented, keeping the vessel upright. But dividing up the storage space creates a new logistical hurdle. During the loading process, the crew cannot fill these tanks at random. The weight distribution must remain perfectly balanced from front to back and port to starboard to avoid tipping the ship while it sits at the dock. This requires a highly synchronized sequence. Heavy-duty pumps drive the crude down the ship's intricate pipeline systems, distributing it through outlet valves called bell mouths to fill symmetrical batches of tanks at the exact same time. Pumping in that much liquid displacement causes dangerous air pressure to build up inside those confined compartments very quickly. To vent that pressure safely while loading, the ship relies on tall structures connected to the cargo tanks below deck, known as masterizers. Mastering these internal fluid dynamics ensures the ship won't destroy itself from the inside out, but it still has to survive the physical threats waiting in the open ocean. Out on the water, the ship faces the constant risk of external impacts. If the vessel strikes a submerged obstacle, or if severe structural fatigue cracks the outer wall, millions of gallons of crude could immediately flood into the environment. Double hulls place an empty gap between the outer seawall and the air cargo hull, so external punctures leave the oil intact. Internally, engineers build cofferdams, empty vertical buffer spaces between adjacent tanks holding different liquids, to prevent cross-contamination. If an interior tank wall cracks, the cofferdam catches the escaping liquid. This completely prevents two volatile substances from mixing, and it provides the crew with a safe, isolated pocket of space to enter and weld the leak shut. By layering double hulls against the ocean and cofferdams between the cargo tanks, structural breaches are fully contained. Catastrophic spills become manageable repairs. Once the ship finally reaches its destination, offloading the crude presents its own physics problem. Crude oil is naturally thick and highly viscous. The cargo tanks are fitted with massive heating coils to warm the oil, thinning it out so the ship's pumps can successfully push it through the pipes. Because ultra-large carriers sit so deep in the water, they are often too massive to safely approach a standard coastal dock. When this happens, they stay offshore and transfer their cargo using subsea pipelines connected to floating buoys, or offload directly into smaller product tankers. But discharging the oil removes tens of thousands of tons of mass from the vessel. Without that immense cargo weight pushing down against the ship's natural buoyancy, an empty tanker rides dangerously high in the water, leaving it highly unstable against the wind and waves. To restore equilibrium for the return voyage, the crew pumps thousands of gallons of seawater directly into dedicated ballast tanks. This water intentionally fills the empty spaces between the inner and outer hulls, forcing the vessel properly back beneath the surface. However, pulling seawater from one part of the world and carrying it to another introduces a hidden biological threat, transporting invasive microorganisms. Before this ballast water is discharged at the next loading port, it passes through an onboard water treatment system to neutralize any foreign bacteria. Achieving this precise buoyant equilibrium ensures the massive ship is safe to navigate while completely empty, without inadvertently destroying the marine ecosystems along its route. An ultra-large crude carrier is an intricate, floating puzzle of physics, fluid dynamics, and thermodynamics. Every individual system must operate in perfect, simultaneous tandem. Massive engine rooms power the vessel, the pump rooms drive the manifolds, and heating coils manage the viscosity. The engineering explicitly anticipates failure at every step. Internal compartmentalization defeats the deadly force of the slosh. Double hull armor defeats the threat of physical breaches, and the active intake of ballast water defeats the loss of buoyancy. The final design of these massive vessels achieves a highly deliberate equilibrium. They are built to fulfill a dual purpose: to protect the global energy supply from the unforgiving ocean, and to protect the ocean from the sheer volume of the energy supply.